These are the miracles of the modern age. Buildings so tall and graceful they defy imagination. Bridges spanning depths of rushing water with powerful girders so slender they seem to disappear into the abutments. These are the miracles we live with and enjoy every day, and they could only have been built from steel. The strength and flexibility of steel is unsurpassed by any other structural material. Steel is light, yet it is strong enough to stretch across great distances with longer spans. Steel gives designers and engineers the ability to fulfill their most imaginative concepts with structures that would be impossible to build with anything else. Steel is not only durable and economical, it allows existing structures to be altered or expanded for new or greater uses. And because fabrication can be precisely controlled off-site, steel is fast to build, much faster than other materials, and it is buildable in any season. Steel also helps preserve the earth because it is 100% recyclable, and it can be used again and again without losing any of its original strength. In fact, more steel is recycled than all other materials combined. Thanks to the power of contemporary electric arc furnaces, this scrap metal can be transformed into high-quality steel in little more than 3 hours. When it has been fired, refined, and processed, it can become powerful beams capable of supporting modern buildings or bridge spans. This electric arc furnace, consuming about 75 megawatts of electricity, just melted about 125 tons of used cars and other forms of ferrous steel scrap in about 60 minutes. The electricity arcs between the carbon electrodes and the steel scrap in the furnace to produce a heat of molten steel. Once the scrap has been transformed into molten steel, specific alloys are added to create steel that has the exact strength and properties required for its future use. Each heat will meet the requirements of the steel specification ordered by the customer, related to the chemistry and composition. Using electronic microscopes and spectrometers, inspectors scan the steel to ensure that every piece of steel has a uniform and consistent composition. Since the introduction of structural steel shapes, improvements in materials and design methods have made a profound difference. If the Sears Tower were built today, it would require 35% less steel than when it was built in 1974. After the scrap has been melted, refined, and tested, the molten steel goes into a bathtub-like container called a tundish. The steel then moves through continuous casters, where it will be made into slabs, billets, blooms, near-net shapes, or beam blanks. In the continuous casters, the steel flows through nozzles into water-cooled molds, where it is cast into a continuous bar. When the steel comes out of the caster, it must cool to 1600 degrees in order to solidify. When the steel is to be rolled or further processed, it will be brought back up to 2400 degrees before it completely cools, thereby saving the time and energy that would be required to reheat steel at a later time from room temperature. This process, like many others in the production of today's steel, is controlled by computer-driven equipment. The steel bar then goes through a straightener, and it will emerge as the finished product. Just think, only a little more than 3 hours have passed since this steel was scrap metal. It has been transformed into high-strength steel, saving our precious natural resources and preserving the earth through the use of recycling technology. After the steel has been produced, every piece of steel must be precisely cut, its holes properly placed, its pieces welded in exactly the right location. Every single bolt in the structure must be located and attached at the proper place, and all this must be exact to 1/16 of an inch, so that the steel members will fit together perfectly at the site. That's why a process called detailing is such an important and integral part of building today's complex steel-based structures. It is the detailer who must develop drawings that are so precise that they will show the fabricator the exact dimensions required for manufacturing the finished steel components that will go into the structure. To accomplish this formidable task, the detailer will take the design prepared by the structural engineer and, on paper, build a 2-dimension or a 3D model of the steel frame of the building or bridge. It is from this model that the detailer will generate a complete list of every member in the structure, as well as shop drawings for all the individual steel pieces. To accomplish this process, the detailer must compute the length of the beams and columns, as well as the bolts and raw material to be used. The detailer must also keep track of every hole in the entire structure. If a change is made in a beam connection or in the hole of one column web, it will be up to the detailer to indicate exactly how that change will affect all the holes in those beams. In addition, if a member has been changed on the shop drawing, the detailer must also change the erection drawings that will be used in the field. All this information is developed with the help of computers, and it can be downloaded to the drill line in the shop or to the angle master to show them how to drill holes for the angles. But it's important to realize that although these critical tasks are done with the assistance of a computer, they are not done by the computer. The detailer's training, skill, and expertise is the key to the process. It is the detailer's ability to translate the engineering drawings of a large structure for the fabricator so that the fabrication shop will know exactly what must be done to prepare the steel. The detailer will also indicate the preparation, cleaning, and painting of the materials, depending on its specification. If that weren't enough, the detailer may also have to consider and take into account shipping requirements, sometimes even the cranes that will be used in the field, and how those cranes will load and unload members from the truck. Before the fabrication shop actually drills and cuts the steel members, the detailer must submit his shop drawings to the engineer of record for approval to make sure that the shop drawings are fully compliant with the engineer's design. It's clear that steel fabrication plays an important role in joining steel members, even before the beams and girders arrive at the construction site. This is one reason why on-site building with steel is so much faster than is possible with other materials. At the fabrication shop, the steel is cut, punched, and pre-assembled as much as possible according to the detailer's drawings. These drawings can be used to generate computer disks that will drive the shop's fabricating machinery to cut and drill the steel with absolute precision. If cutting is necessary, the operator inputs the size and the desired member. The stock lengths of steel will enter the cutting machine by conveyor. An automatic arm stops the stock at exactly the right point, and the blade cuts the steel. The piece will then be labeled and rolled out. From the cutting area, the steel members will travel on a conveyor to the next station, where holes will be drilled to make the bolted connections. Here again, these critical processes are precision controlled by computer. The machine operator inserts the disc into the computer as the member is fed through the drilling machine, pushes a few buttons, and the computer takes over. As the steel automatically goes through the machine, its exact location will be monitored by laser measuring devices, so it will stop precisely where the holes must be drilled. All of the holes will be drilled in one pass as the column goes through the machine. The operator is able to see different views of the member on a small monitor, noting the number, location, and size of holes needed, as well as the precise location of the drill bit. When the holes have been made, the member will travel on conveyor to the next station. The coping machine burns steel to cut members like a saw, or it notches the steel and makes holes. Here again, the operator inserts the proper disc in the computer to initiate the process, and the piece automatically stops at the location where the precise burning operations will take place. Usually, edges that are flame cut by the coping machine are smooth and require no additional work. From here, the steel member goes to the layout station, where angles, plates, and other connection parts are bolted or tack welded. Today, high-strength bolts and welds have made joining steel members faster, more economical, and more reliable than ever before. If the piece needs welding, it will be taken to the welding area, where the welding can be done. There are other areas in the fabrication shop where the pieces needed for joining steel members are produced. For connections that require angles, stock lengths of angles are automatically delivered to an angle machine, which will cut them to the desired length and punch holes at the appropriate locations in one pass. Torch cutting plates is another operation performed by computer-operated machines in the fabrication shop. Shearing plates, punching holes, and bending steel members are other processes that take place at the fabrication shop. The piece may require cleaning and painting before being shipped. When a piece has been through all the processing called for in the detailer's instructions, it is taken to the yard, loaded onto a truck, and transported to a job site or storage yard. Because there is often not enough space on the job site to store all the fabricated steel needed for the job, the process of delivering, hoisting, and placing steel has to be carefully planned so that the pieces will be delivered to the site in the order in which they will be erected.